Okay, here's another example. I've labelled it example 2. We've got point charges Q1 and Q2, you see positive and minus, of plus 12 times 10 to the minus 9 coulombs, which is that one, and minus 12 times 10 to the minus 9 coulombs, which is that one, respectively, are placed 0.1 meters apart. So here you can see in this diagram, that's 10, and that's 10, okay? So this diagram is all given here, all the measurements are given, as shown. Compute the electric fields due to these charges at points A, B and C. So what you've got to do is, given all of these values and the charge values here, 12 times 10 to the minus 9 and minus 12 times 10 to the minus 9 plus 10 centimeters, this is 10 centimeters, C is 10 centimeters here and 10 centimeters from here, and the distance between them is 10 centimeters. So you can see, as a clue, that's an equilateral triangle, so that's going to help you. I'll put in an angle there to give you another clue. And here's the point A, and here's the point C, and here's the point B. So we're going to be working out these field values, okay? So that's what you need to work out. So here's the measurements between them. So you got between B and this charge is 4 centimeters, and between A and Q is 6 centimeters, and between A and minus Q is 4 centimeters. So given all that information, see if you can calculate the electric fields due to A, B and C, and then I'll go through it for you. Okay, let's go through it. Okay, the solution at point A. So let's look at point A first. Let's work out what point A is. At point A, the vector due to the positive charge Q1 is directed towards the right. So this charge here is pushing that towards the right, okay? In other words, when we got positive charge, we're saying that the force is in this direction, okay? So the field is in this direction, because that's positive, is pushing that. You know, all the field for positive charges, remember, are all going out, and when you've got a negative charge, all the fields coming in. That's the important thing to remember here, really. So for A, looking at Q1, obviously the field is in this direction, and its magnitude is 9 times 10 to the 9 Newton per meter squared to the coulombs squared, which is, that part there is the K constant, and then obviously you've got the charge above divided by the this distance here. In this case it's 6 centimeters, so we put 0.06 underneath and square it. That gives us this distance. Remember, we're using the equation for the field here, which is 1 over 4 pi epsilon naught, and we'll just place that as, you know, just put the number in there for that. And then of course that was the charge value, the big Q value we saw in our formula before, and then we have R squared, which is that value there. Okay, if you plug all those numbers in, you'll get for E1, for this we're going to call this the field attributed from this charge, we're going to call that E1. E1 is equal to 3 times 10 to the 4 units per coulomb. The vector due to the negative charge, Q2, so now we're going to look at the charge Q2. Now, of course, remember, the fields, when we're looking at negative charge, the fields are going inwards. They're going into the charge. So obviously that means that A fields are pulling towards this, okay? So the field is in this direction again. So it's, you can see that they're both going in the same direction now. So if we now just concentrate on this charge, we do exactly the same thing. We've got the distance 4 centimeters apart here. So we do exactly the same thing. The vector due to the negative charge Q2 is also directed towards the right, because of the reason I've said, the electric field will go into negative charges. So then we've got the K constant here, which is 1 over 4 pi epsilon naught. That's that number. Again, we've got the 12 times 10 to the minus 9. And, you know, we don't have to worry about the minus and plus signs here, because we know what we're into the direction here. That's the important thing. So then underneath, we've got this distance is 4 centimeters, 0.04 meters squared. Remember to get your SI units, to get the units right, you know, that's centimeters, so we want meters. A simple thing, but you know, easy to slip up on that. If you plug in the numbers, you end up with 6.75 times 10 to the 4 newtons per coulomb. So the resultant force is the sum of both of those, obviously. So it's the sum of the contribution from that one and the contribution from that one gives us the total field at point A is then basically the 3 plus the 6.75. So I've just put those in brackets, and obviously the units outside are the same. 10 to the 4 newtons per coulomb. And if you plug in the values, you end up with 9.75 times 10 to the 4 newtons per coulomb. And that's in the direction to the right. So that's the A. So you found the A. That's the answer to the EA, okay? Right. With exactly the same reasoning, we'll do the same with B. So obviously we're going to find the contribution from this one. Remember, for this one, the fields are going in that direction, and for that one, it's going in that direction. You can do exactly the same process, so I won't go through it again. You can do that. It's really easy. Just do the same process again. And for EB, you end up with it going in that direction. It turns out that it's in that. You can imagine, because this this positive field is much stronger than, they're both the same charges. So obviously this positive electric field that's all going out is much stronger than that one. So obviously that contribution is going to be much greater than that one. So that's why you end up with a resultant field going in that direction. Okay, it's quite obvious really. So then if you plug in all the values, you end up with 6.2 times 10 to the 4. So that's your EB. Now C is a little bit different. Now there's a trick here with C. Well, remember, you've got an equilateral triangle, okay? Now remember, the contribution of the fields going in this direction, you can imagine going up. So, you've got fields going up, but then you've got the contributions going down. And so you can see that if you think about point C here or here, they're exactly in the middle. They're obviously, all the Y ones are just going to cancel, yeah. So the contribution is just going to cancel. So you don't have to worry about the Y direction. So all you got to worry about is, which direction is it going in this way? Okay. So what you can do is now at point C, the magnitude of each vector is 1 over 4 pi epsilon naught again, which is the K, 12 times 10 to the 9, and the distance between them is 0.1 meters squared, so that's 1.08. Now, of course, because we're right in the middle here, we can see that there, and because that there is being attracted to that, and in a way it's being pushed by that, so you can see just by reasoning, because obviously that's pushing in, the field's going that way, and that one's pulling, so that one's going to pull as much as that one's pushing at this point, yeah. So it's going to be twice. So if we just work out 1, it's just obviously going to be twice that, yeah? And that's really what the answer is. So I think that's what I've said here. The direction of these vectors are shown. Clearly, EC in the Y directions cancel, which we just said. And we have the X contribution from both charges. So, yeah, as I've just said. So that becomes 2 times 1.08 times 10 to the 4 newtons per coulomb. And here, of course, what you need to do is you're working out this, so you need to work out this actual component here. We've got the force of this one here, which we've calculated is 108 times 10 to the 4. Okay, just looking at 1, and we just multiply it by 2. Yeah. So given that we've got that one, and cosine theta equals adjacent divided by hypotenuse. Okay. We can say that there then obviously is hypotenuse times cosine theta. Okay, so we've got that value there. So then we can just plug all those in, and we can then where cosine theta equals. I mean, the other thing is we know what cosine theta is because we know this distance. This is the trick here. This is an equilateral triangle, so we know that it's length of 5 by 10. So that's good because that can then give us this angle theta, okay? So we can find the angle theta because we know it's 5 over 10 because we just drop that down the middle. That's 10, a unit 10 long, yeah? So we drop that down the middle, that's 5. So it's 5 over 10, that's 0.5. So we've got cosine theta. Since we've got cosine theta, we can just put that straight in there. And then we know it's, as I say, because the contribution from that is pushing as that one's pulling in the same amount. That one's going up and that one's going down. They're both going in that direction, okay? So basically it's 2 times. And you put the 0.5 in there and you get the answer to the right.